Okay, welcome back. We were talking about Rabin, Street, and parity conditions, and we have these three issues. Each of them deserve a couple of hours, a complete course, but we will survey some results. And we will start with expressive power and succinctness. And here what we want to see is that indeed these conditions result in classes, expressiveness classes that are as expressive as non-deterministic book keyword automata. And how are we going to do it? We are going to show translations, for example, from a non-deterministic Rabin word automaton to a Bookey automaton. So how can we do it? We have a Rabin automaton, a non-deterministic automaton. It has alphabet, state space, set of initial state, transition function, and acceptance condition. It's a non-deterministic automaton, and the construction is not going to preserve determinism, and we are not surprised because we know that deterministic Rabin is more expressive than deterministic Bookey. So we will see exactly where we lose this, when we lose determinism if we start with a deterministic automaton. And acceptance condition alpha, I remind you, alpha is a set of pairs, left and right, pairs of states up to LK, RK, and Eran is accepting if there exists a pair such that we visit Li infinitely often and visit Ri only finitely often. And it is not hard to see that since there should exist an I between 1 to k, then A can be viewed as a union of automata, a union of automata with a single pair. If I define alpha I to include only the pair Li, Ri, and then I define the automaton AI as a non-deterministic Rabin word automaton that has a Rabin automaton. Sometimes it is called like, it is denoted like that to emphasize that it has a single pair with acceptance condition alpha I. Then A is really the union of these alpha I's. And this is good for us because it means that we have already seen that Bookey is closed for union, then it's good enough for us to translate each of these AIs to a Bookey automaton. So let's do that. Let's take AI. This is a Rabin automaton with a single pair, and translate it to some AI prime, which would be a Bookey automaton. And this is easy because here the automaton should accept words that visit Li infinitely often and visit Ri only finitely often. So what are we going to do? Something that we saw similar things already. We are going to start with a copy of all the state space. So this is our copy Q, or let's call it Q0 because we want to keep the I. So this is the zero copy of Q. And then at some point we guess that we no longer visit Ri, Q minus Ri. This will be the ice copy because I want to maintain the states of the AIs disjoint. And in this copy, I want to visit Li infinitely often. So more formally, my state space here will be Q with 0. Whenever I see a state, I can guess whether I'm staying in Q. And if this state is not in Ri, then I can move to this copy. So the state space is Q labeled, attributed by 0, and Q minus R attributed by I. And the acceptance condition, alpha I prime, the Bookey acceptance condition of AI, will ask me to visit states in Li in the second copy that I marked I. So this is going to be a Bookey automaton equivalent to AI. What about A itself? I can take the union of these automata, but it's a bit nicer to say that we will have a single joint copy for all of them. So copy 0 in which a loop is unified for all the pairs. And from here, I can jump to Q minus L1. This will be the first copy, or to Q minus L2. This will be the second copy. Here I loop only with states that are not in L1. Here only with states that are not in L2. And we do it for all pairs, Q minus Lk. And within these sets, the good sets, I want to visit Ri, R1 here infinitely often. Here I want to visit R2 infinitely often. Here Rk, and so on. So what we got is an automaton if I want to consider the blow up. So if I started with a Rabin automaton with n states and index k, and I end up in a Bookey automaton with k plus 1 copies. So I have n times k plus 1 states in the equivalent Rabin automaton. Where do we introduce determinism, non-determinism? In two issues. One is choosing the pair. So I chose whether to try and get accepted by the first, second, and so on pairs. But not less important, I also made a guess when to jump. And this is the crucial guess. This is the crucial guess. So even Rabin with a single pair, I cannot simulate with a deterministic Bookey automaton because I have to guess where I'm stopping visiting, where I stop visiting states in L1. So Rabin is as expressive, the non-deterministic variant, but it may be more succinct. I need fewer states. So this is what happens with Rabin. In street, it is tempting to do something that is dual, right? Because in street, I want all pairs. So I want to translate NSW to NBW. Now I want for all I that infinitely many visits in Li will imply infinitely many visits in Ri. But this intersection is not good enough in this case. And what I really need, so the NBW, if I start with A and I go to A prime, so A prime need to guess a subset of the indexes, a subset I of 1 up to k. And when we guess this subset, this is the subset of indices such that I is in I if and only if the run visits Li infinitely often. So I'm guessing for each pair how it is going to be satisfied. Is it going to be satisfied by visiting both Li and Ri infinitely often, or it is going to be satisfied by visiting Ri only finitely often? And it's interesting to think, and you're welcome to think, why intersection wouldn't work. We can say that no, it does not work to define A prime as the intersection of I between 1 to k AI if I define AI the same way I defined it with Rabin automaton, with a single pair. Why doesn't it work? I want you to think, but it has to do with the fact A is non-deterministic and different pairs may be satisfied in different ways. So the blow up that we get when we translate an NSW to an NBW, so I start in a street automaton with n states and k pairs. Now the blow up will be exponential in k. So it will be something like n2 to the k. If you want the exact expression, it will be n plus 2 to the k times n times k. Because once I guess a subset, I need to make sure I'm visiting all the states in all guessed sets. So we won't get into the details now, but the blow-up is exponential in K. And of course, whenever we have such a bound, we need also a lower bound, right? We say now that street automata are more succinct than bookie automata. So whenever we have such a result, we have two results. One is an upper bound, something that tells us that such a translation exists, but we also need a lower bound, a family of languages that can be recognized by a small street automaton, but needs a large and exponentially large bookie automaton, and there are such proofs. So this is essentially what we wanted to say about translating street and Rabin to bookie automata in the non-deterministic variant. Talking about succinctness, we could ask also what happens in the deterministic variant. What happens, for example, when I have a deterministic Rabin word automaton and I want to translate it to a deterministic bookie word automaton. And immediately I should add when exists. What's the blow up? When exists. Because not all deterministic Rabin automata have equivalent deterministic bookie automata. The question, suppose there is one, what would be the blow up? And here we have some surprising results. The underlying notion in all of them is typeness. And what is typeness? Let's demonstrate it with Rabin and bookie. We say that Rabin is called bookie type. What does it mean? It means that if L is in DBW, if I have a language that can be recognized by a deterministic bookie word automaton, and A is a DRW, deterministic Rabin word automaton for L, then I know that some bookie automaton for L exists. Now the then will tell me that then there is a DBW for L on the same structure, on the structure of A. So if a Rabin automaton, a deterministic Rabin automaton, recognizes a language that can be recognized by a bookie word automaton, then I can define an acceptance condition on the state space of A and get this bookie automaton. So there is actually no blow up in this translation. No blow up. If there is a bookie automaton, then there is a bookie automaton on the same structure. And yeah, we saw, for example, the automaton for infinitely many ones. So that was S1. Here I had S0. I have a Rabin automaton. The language of infinitely many ones can be recognized by a bookie automaton, and there is a bookie automaton on the same structure. And this is valid for all languages that are recognizable by bookie. So Rabin is bookie type. Street is not bookie type. Street is not bookie type. For example, something we saw. We saw a street automaton for infinitely many 0 and infinitely many 1. This is a language that can be recognized by a bookie word automaton. We saw a street automaton with 2 states from it. Actually, this automaton, I can define a state condition like a generalized bookie condition. I can say that I want to see S0 infinitely often, and I want to see S1 infinitely often. So this is a street condition on top of this automaton that will give me this language, and I cannot define a bookie condition on top of this structure for this language. So Rabin is bookie type, street is not bookie type, street is co-bookie type, So tightness is a useful notion that tells me that for the deterministic setting, I don't always have this blow-up. In the non-deterministic setting, we have a complete picture of succinctness and the blow-up in translations. So this is what we wanted to say about expressive power and succinctness. Now let's move on to decision procedure. There are all kinds of questions we may ask about our automata. For example, the most basic one is emptiness. Emptiness or non-emptiness. So I have an automaton A given A of any type, and I want to know whether the language of A is empty or non-empty. What to do? So one thing to notice, and the issue that is relevant for us also in the context of the several acceptance conditions, is whether we pay for more in the more expressive acceptance conditions. And another source of blow up is the fact we talk about non-deterministic or deterministic automata. What do I mean? Think about the non-emptiness problem or the emptiness. So it will be more convenient to talk about non-emptiness. We want a witness to a word accepted by the automaton. So how would you check that a Bookey automaton, a non-deterministic Bookey word automaton A is not empty? In order for the automaton not to be empty, we need to have some pass from an initial state to an accepting state that is reachable from itself. Let's write it. A is not empty if and only if there is some state Q in alpha such that Q is reachable from Q0 and from itself. Why? Two directions, right? If we have such a state Q, we have a non-emptiness witness. If this pass is labeled by U and this pass is labeled by V, then I know that U V omega is accepted by A. The other way around, if there exists a run that accepts some word, then there must be a state in alpha that is visited infinitely often. This state in alpha must be reachable from itself and from Q0. So I have two directions. And in terms of complexity, what does it tell me? It tells me that the non-emptiness problem is first in n-log space. Why? Because I can guess this Q and then do two reachability checks, and reachability is in n-log space. And I can also solve it in linear time. And the best way to do it is to partition the state space of the automaton to strongly connected components and check, let's write it. Is there, this is what I need to check, is there a maximal strongly connected component S? Yes, so a component is a subset of the state space. All states are reachable from all states. So and I want to check whether there is a maximal strongly connected component S such that S is reachable from Q0 and S, its intersection with alpha, is not empty. And once the intersection of S with alpha is not empty, I need this, I didn't write, this maximal strongly connected component S should be not trivial. It should contain at least one edge, and therefore it contains at least one cycle. So once I reach this S and this S intersects alpha, I know that I can generate a path that visits alpha infinitely often. And the reason I insisted on maximal is because I have Tarjan's algorithm that finds these strongly connected components, the maximal ones, in linear time. So I can do this in linear time. And this is what I do with Bookie. And the thing I started to say earlier is the fact that the automaton was non-deterministic didn't play a role here, right? The same algorithm would work for Bookie, or more interesting, there is no easier algorithm for deterministic automata. So in the context of the non-emptiness check, we got non-determinism for free. The complexity is the same. The problem is n-log space hard, both in the non-deterministic and deterministic variants. So we got the non-determinism for free. And now when we talk about other acceptance conditions, if we want to check, for example, non-emptiness for Rabin automata, for non-deterministic Rabin word automata, or for street automata, again, we can ask whether it will stay n-log space complete and in linear time. So what would you do? How will you check non-emptiness of Rabin? One possibility is to take the Rabin automaton, nk, translate it to a Bookie word automaton with n times k, n plus 1 states. So it will be linear, but linear in n times k. So it will be polynomial, and in street it will be even harder, because we know that if we start with street, we will end up with Bookie with exponentially many states. So there is a question whether we can do better. And the answer is somewhat involved. There are algorithms, and there is still ongoing research on non-emptiness algorithms, especially for street. And again, unfortunately, we only have to mention them. So they are all in polynomial time. In fact, in Rabin, I stay in n-log space. In street, I have to jump to p time. I can no longer just remember a single state. It's more complicated than reachability, but p time is good, but less good than Bookie. I'm not talking about parity here. Parity is more interesting in the context of games. I'm sure you will hear about it a lot in the course of games. But since parity is a special case of Rabin, then all the good things we say about Rabin apply to them. Other decision problems that may be of interest is universality. In universality, we ask whether A accepts all words, and related to universality is containment. And in containment, we get two automata, A1 and A2, and we want to check whether the language of A1 is contained in the language of A2. And it's not hard to see that universality is a special case of containment, right? A is universal if and only if the automaton that accepts all words, I'm drawing here a Bookie automaton, we can clearly draw also other automata, is contained in L of A. So how can we solve containment? So we know that two sets, if I have A and B, then A is contained in B, if and only if the intersection of A with the complement of B is empty, right? I have no word that is both, or no element that is both in O and not in B. which means that in our case of automata, L of A1 is contained in L of A2 if what? If the language of an automaton that accepts A1, its product with the complement of A2 is empty. So in order to solve containment, and containment is a very important problem in the context of model checking, because what we really want to check is that the language of our system is contained in the language of the specification. So it involves two operators. It involves complementation of A2, of the automaton on the right-hand side, and it contains product. On top of them, we have to perform a non-emptiness check. So this is, we are not going to say much more than this. We are going just to mention that the problem is p-space complete. It is p-space complete since complementation will cost us an exponent, and then non-emptiness is n-log space. So we apply an n-log space algorithm on something exponential, and we know how to do it on the fly. So we get a p-space algorithm, and it's similar, some of you probably saw in your courses on automata on finite words, that universality is called all-NFA, right? So all-NFA is p-space hard already for finite words. But what I do want is this to take us to the last thing we will mention, and I'm saying mention again because we are not delving into the details, just solving some results, and this is determinization and complementation. Determinization and complementation. And this is a very heavy topic, and we need it, we really need it, because, right, we had our picture of expressive power, and here we have the NBW, and we want to show that we can take a Bookey automaton and translate it to a deterministic Rabin or street or parity word automaton. So how to do it? When we work on finite words, so when we have an automaton on finite words, we already mentioned we know how to determinize. We get a DFW by applying the subset construction. We start with state space Q, and we go to state space 2 to the Q, and when we are in a set of states S here, it means that in my non-deterministic automaton, I had a run that could reach each of these states, right? So this is the subset construction, and a set is accepting if it contains an accepting state in the original non-deterministic automaton, because then there exists an accepting run. Now I want to take a Bookey automaton and translate it to something deterministic. And we already saw that we cannot do something on top of the subset construction. Sometimes it wouldn't work. With Bookey, it wouldn't work. We didn't see more than that. And the construction, there are all kinds of constructions. The most famous one is the one by Safra. It is famous for good reason, because it was the first one to achieve the tight bound. The tight bound is 2 to the O of n log n. So it's more involved than the subset construction, and Safra did it with the Rabin condition. Today, we have also direct constructions to parity condition. And 2 to the n log n means that on top of the subset construction, so in the subset construction, we only have a set S, right? We have S. In the construction by Rabin, we have S, this is the subset, plus attributions, plus additional information. Which kind of additional information we need in order to simulate a Bookey automaton? right? A Bookie automaton has many runs, and we want one of them to visit alpha infinitely often. So you can imagine a tree, and in fact, it can also be a DAG of all runs. And we need to know whether there is a path here in one of them that visits alpha infinitely often. If we do the subset construction, we only get these levels in the run, right? And we already know that it is not good enough to say that a level is good if it contains an accepting state, because different, let's draw an example. If this is the tree of all runs, you can imagine a situation where from here, I always branch to an accepting state, but there is no accepting run. I have infinitely many levels with accepting states. All levels may even have accepting states, but there is no single path that contains infinitely many accepting states. So my additional information should enable me to ask a question about the existence of a path. So the suggestion of Safra was to arrange this additional information in a tree. These are called Safra trees. So this is a single state in the deterministic automaton, and the states are labeled, this is the subset of state, this is S. On top of it, we add a structure that tells me something about visits in alpha of the states that appear. So don't let the fact that there are many states here bother you. Yes, this is an automaton. This set of states correspond to a level in the tree. So I have all these states in the same level in the tree. Some of them are accepting, some are not. And the tree structure tells me something about events that happen on the way to this level. And now I'm going to use the Rabin condition for in two ways. So remember, in Rabin, I have L and R. L, I want to see infinitely often. R, I want to see only finitely often. So I'm going to use R in order to make sure that eventually I am starting to follow a single path. So R will guarantee the fact that eventually I'm getting stuck in a certain set of states, will tell me that eventually I'm follow a path in the run tree. And then I'm going to use L in order to say that this path has infinitely many visits in alpha. So this is really the very general idea. The construction itself is complicated. Some people say that, it is too complicated. And the reason this is the blow up is because this is the number of such different trees, is the subset construction plus additional information. And by now we also have translations that go directly to parity. So this is a construction by Peterman in 2006, and many more translations, both from Bookie, non-deterministic Bookie, to deterministic Rabin or parity, and also translations among deterministic automata with different acceptance conditions. So this was a very brief introduction to automata theory, and we will say more in the live talks on Monday. See you then.